this whole chapter has got so much to do with limits. I feel like we're kind of back where we started again, because we started calculus with limits. And sometimes it's like I wish I could teach all the limit stuff at the beginning, except you don't know derivatives yet, and so you can't teach L'Hopital, and you don't know, yeah, anyway, there's just too many things that you can't teach. But we're back to limits again, as is defined as a growth rate. Okay, so one of the things we need to learn how to do in this chapter is our objective. Is to compare two functions, f of x to g of x, and we want to be able to make a determination which will reach infinity first, if you could get there. And so that's called which will have a higher or a faster growth rate. It's like comparing two people, you know, and who's going to get to their adult height first. Everybody's going to eventually get to their adult height. It's just some people get to their adult height in 6th grade, and then they're done growing, and other people don't get to their adult height until they're like in college. They're still growing in college yet. And so that's our objective today, is to compare the growth rates, and we do this with limits. All right, so if that's our objective, then here's our procedure. It feels like I'm writing a lab report. All right, so what we're going to do is we're going to take the limit as x approaches infinity, and we're going to stack f of x over g of x. We're just going to compare their ratios. And there's only 3 different results. Okay, one result would be that you get a limit. Okay, what that means, if you get a limit, the implication then is that their growth rates are equal. So that f of x and g of x have equal growth rates. So that's one scenario. When you compare them, you actually get a limit value. Okay, what are some other scenarios? Okay. What other results could I get when I take the limit of something? Okay, I could get infinity. If I get infinity, can you deduce the implication on that? F of x isn't necessarily greater, but it has a greater growth rate. Okay, so then f of x has a greater growth rate than g of x does. Okay, and then, so the last option, if I don't get an actual limit and I don't get infinity, then what's my only other option? I get 0. I should have specified that L can't be 0. Yeah, maybe I should. As long as L's not 0. Okay. Then the implication on that is that g of x has the greater growth rate. Okay, now, there's a shortcut to doing the limit, which will be great if this is a multiple choice question and you don't have to show your work. So we're going to do both. I'll show you the shortcut, which would be how you would answer a multiple choice question. You just have to choose something quickly. But then if you have to justify, justify which function, then you have to actually do the limit process. Okay, so here is the shortcut. that's n-fepl. N to the n, F-E-P-L. All right, this is just a quick little acronym to help you order things going from fastest to slowest. The fastest functions are n to the n functions. Okay, that's like x to the x, or x to the x plus 3, or something that's in the format where it has both a variable base and a variable exponent. The F stands for any factorial function. That grows really fast, just not as fast as x to the n functions, those super exponentials. E is just a regular exponential. That grows pretty fast, but not as fast as a factorial. You understand what I mean by factorial with the exclamation point? Yeah. Okay. As long as your base is greater than 1. Because we already saw with Cassidy, if the base was less than 1, like 0.9, then it's not growing fast at all, it's shrinking. Okay, so the base has to be greater than 1 if you're talking about exponential. All right, P, polynomial. So cubics, quartics, parabolics. And then last is logs. Okay, logarithms grow. They just grow very slowly. And some people say, well, why not linear? Linear has a constant growth rate, right? A linear has a slope that's just steady. It's not a curve. So we're only comparing the things of curved functions. So n-fepl would have you just help you kind of put those in order. So an example maybe of a multiple choice would be something like order the following functions according to their growth rate. And then you'd have multiple choice where they were all different orders and you just have to pick the right one. Okay. All right, so the functions I'm going to give you are 2 to the x, x to the 2, e to the x, the natural log of 2 to the x, and x to the x. All right, put those functions in order according to n-fepl from fastest to slowest. Okay, not asking you to prove anything, not asking you to justify anything, just asking you to order them. All right, so thinking from fastest to slowest. What would you categorize as the fastest growing function of the 5 functions that were listed? Okay, x to the x. That is going to be a super exponential where it's going to grow the fastest of all of them, and the steepest growth rate. All right, what would come next? Okay, so we've got how many different exponential functions here? Okay, I've got 2, e, and natural log of 2. Okay, now since there are no factorials, but there are 3 exponentials, and you need to order them compared to with the value of their base. So we've got a base of 2, we've got a base of e, which is 2.7, and then what about the natural log of 2? Okay. All right, it's point what? Okay, which is less than 1. Okay, so next is going to be what? Okay, e to the x, then 2 to the x. Okay, then what? Okay, good. Then x squared. And then finally, the natural log of 2 to the x, because its base value is less than 1. It's actually not growing at all. Yeah?
What would be like a number example or a
Okay, a simple one would be like x factorial.
Okay, so
it would be x
factorial sign.
minus 1 factorial, yeah.
Okay.
Yeah, for sure.
Does the shortcut always work? Like, is there any special like?
I suppose if you had two that were equal.
Oh, I have a question. Like, how about comparing square root of the x and log of x?
Let's do it. Okay.
Why is x squared before the natural?
Because if you even just think about their shapes, okay, so x squared is a parabola going up like this. The natural log of 2, because it's a number that's less than 1, it's a decreasing function. So it's not growing at all. It's decaying, it's decreasing. So because it has a negative growth rate, we definitely put that at the end. All right. Okay. So Bobby, let me do the examples I planned, and then we'll compare square root of x. What did you want to do? Square root of x to log of x? Okay. So then we'll try comparing that. That was my hunch. That's my gut. Yeah. Question? Oh, okay. All right. So let's prove the growth rate of e to the x and x squared. Now, according to NFEPL, we already know which one has the faster growth rate. So you can prove it in either direction. You can either put e to the x on top of x squared, or you can put x squared on top of e to the x. You'll get a different result, but the result should lead to the same conclusion. So it really doesn't matter how you're going to do that. So the way I planned it, I'm just going to do e to the x over x squared. Okay. When I take the limit of that, I plug infinity in, and I get infinity over infinity, which is indeterminate, which means I need to apply L'Hopital. The derivative of e to the x is still e to the x. The derivative of x squared is 2x. Okay, again, I get infinity over infinity a second time, so one more. And this time, I'm going to get e to the x over 2. 2 is a constant, so I'm going to get infinity divided by 2, which is still infinity. I love that. I love that you can split infinity in half and still have infinity left over. Since the result is infinity, we look back at our procedure. Okay, when the result is infinity, that means that the numerator had the greater growth rate. So therefore, e to the x has the greater growth rate, which we knew anyway, but we're just justifying it. Oh, that is like scientific shorthand for the word therefore.
What's the difference between 3 dots and then 3 dots?
Oh, that is, yeah, that's saying that it's absolutely must be equal to. That would be part of an equation. This is just more of a statement. Okay, all right. No, so if I had done it the other way around, I would have ended up with 0, which then would have told me that the denominator was greater, but if I'd put e to the x, it would still tell me that e to the x had the greater growth rate. Okay, so how about compare x plus sine of x and x. Okay, which one has the greater growth rate of those two? All right, so it's arbitrary. X plus sine of x over x. I don't want to plug infinity in necessarily to this. I'd rather do some algebra first, which would be divide by the highest power of x. So I end up with 1 plus the sine of x over x. Okay, the limit of sine of x over x as x approaches infinity is 0. So 1 plus 0 is 0 is 1, which gives me an actual limit value. So this thing would converge to 1, which would mean what about the original two functions? They have the same growth rate. Neither one has a growth rate that exceeds the other. So therefore, x plus sine of x and x have equal growth rates. All right. Bobby, you want to do square root x compared to, does it have to be log or do you want to do natural log? Okay. Do you care which one we put on? Okay. I have a feeling it's going to be that the square root of x has a higher one, so I'm going to put that one on top. But okay. Well, first of all, I get an indeterminate form. Okay, so we're going to need L'Hopital. Okay, so that'll give me 1/2 x to the negative 1/2 over 1 over x. Yeah? Okay, so let's clean that up a little bit. All right, so it is 1/2 x to the what? I think it's multiply by the reciprocal, right? So this is 1/2 x to the negative 1/2 times x over 1. So I just get 1/2 x to the 1/2. Okay? And so, therefore, the answer to that is infinity, which means square root of x grows faster. Yes, ma'am?
Why is the x to the 1/2 in the numerator?
It's not. It is.
With the 2x.
No, it's. Okay, it's 1/2 x to the negative 1/2 times positive x to the 1. That's this. I moved. This is x to the 1.
Yeah, but what about x to the negative 1/2?
Right. No, because the rule is you add exponents. So you get 1/2, and then negative 1/2 plus 1 is positive 1/2.
Okay.
You add the exponents together.